bisection method is one method for solving nonlinear equations. Without loss of generality, we will consider the problem of finding the solution to fx equals 0. You can see that an equation you might have something that's non-zero on the right-hand side. But you can always move the non-zero things on the right-hand side to the left-hand side. For example, x squared equals 2 is the same as x squared minus 2 equals 0. So how can we use the bisection method to find the point where fx is equal to 0? Let's suppose that fx is a continuous function on the region from a to b. And further, fa and fb have opposite signs. By the intermediate value theorem, there must exist a point C that's in the interval from a to b that satisfies fc is equal to 0. So there must be a point C where the function intersects with the x-axis. The bisection method begins with an initial bracket AB, where the solution may lie. And it iteratively narrows down the bracket by half until a solution has been isolated as accurately as desired. In other words, when we reach a pre-specified tolerance level. Tolerance is the error that we can tolerate. Specifically, the procedures are as follows. In step 1, we compute the midpoint of the interval from a to b. This is given by x equals a plus b divided by 2. We will check the sign of f evaluated at this midpoint x and see whether the sign agrees with fa and fb. If fa and fx have opposite signs, it means that the solution C actually lies in the interval from a to x. So we will replace the bracket a to b with a to x. Otherwise, if fa and fx have the same signs, it means that the solution C lies between x and b. So we will replace the bracket a to b with x to b. We will iterate these two steps until b minus a is less than or equal to a tolerance level that we have specified. In other words, when the interval becomes narrow enough. So here is a graphical illustration of this. On the left-hand side is the first step, and then on the right-hand side is the second step. We can see that the original interval is from a to b. We find its midpoint, and we calculate what is f evaluated at this midpoint. Then we can see that fa and f of the midpoint have the same signs, so we will cut this interval to only include the right-hand part. So in the next iteration, the midpoint becomes the new a, and the interval becomes the interval from this original midpoint to b. In the next iteration, we do the same thing where we find the midpoint, evaluate f at the midpoint, and compare the signs of fa and f at the midpoint. This time, you can see that they have opposite signs. So we will narrow down the interval to this left half. One of the issues we might care about is the rate of convergence of these root finding or other algorithms. Let x star be the true solution to fx equals 0. That's the thing we're trying to approximate. And let us use xk to denote the solution in the kth iteration. Then we can define ek, which is the error in the kth iteration, as the difference between xk and the true solution x star. For methods that maintain an interval containing x star, such as the bisection method, error can be defined as the length of the interval, in other words, b minus a in the kth iteration. The algorithm is said to have rate of convergence r if the limit as k goes to infinity of the ratio between error in the k plus 1th iteration and error in the kth iteration length to the rth power is equal to some constant c that is non-zero and finite. Intuitively, convergence rate describes the rate at which error decreases. For example, if r is equal to 1, it is said that the algorithm converges linearly. If r is less than 1, it means that the algorithm converges sublinearly. If r is greater than 1, we say the algorithm converges superlinearly, and specifically, if r is equal to 2, we say the algorithm converges quadratically. For the bisection method, the interval length ek reduces by 1/2 in every iteration. In other words, for any k, the absolute value of ek plus 1 divided by ek to the first power is equal to the constant 0.5. As you can see, since this power here is 1, the bisection method converges linearly with r equals 1. Let's see an example where we will apply the bisection method to solve a nonlinear equation. This example is taken from the textbook. Okay, so here is the problem. Suppose we want to find the solutions to the following nonlinear equation. I will not attempt to read it, but you can see it by yourself. Here, y is the variable, and a and n are parameters, where a is a constant and n is an integer that's greater than 2. Let's note that we can move the things on the right-hand side to the left-hand side. So this nonlinear equation here is equivalent to the quadratic equation of fy, which is equal to y squared plus blah, 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 minus n plus 2 is equal to 0. So let's first create a function for fy. This function essentially takes inputs of y, a, and n, and it computes what fy is equal to. We will numerically solve fy equals 0 for the case when n is equal to 0.5, a is equal to 0.5, and n is equal to 20. And we will use the bisection method with the starting interval b0, b1 equals 0 and 5n, and a tolerance of 0.0001. One thing to note is that if you read the textbook, they use the tolerance that is equal to dot machine double epsilon to the 1/4 power. So this is essentially the machine precision, that is the smallest number in R or on your computer, such that 1 plus that number can be differentiated from 1. So this is something that's built in R, and if you look at what this is equal to, it's around 0.0012. So it's quite close to the tolerance level we use. So let's first specify some objects. So we said a is going to be equal to 0.5, n is equal to 20, and we'll start the interval with b0 equals 0, and the right-hand side of the bracket is b1, which is equal to 5 times n. And we'll create a object epsilon to store the tolerance, and that's set to be equal to 0.0001. One thing to note is that instead of expressing the error as the length of the bisection interval, the book actually expresses the error in terms of the difference between f evaluated at the midpoint and 0, instead of the length of the interval b1 minus b0. So let's try to be consistent with the book and use the former, which is the f function evaluated at the current midpoint. Now let's initialize the y and the fy's. So we set the y to be a sequence from b0 to b1 of length 3. What you can see is that y will be a length 3 vector, where the first entry is b0, the left side lower bound. The second entry is the midpoint of b0 and b1, and the third entry is b1. Then we will calculate fy, which is the function of f evaluated at these 3 possible y values. We will also initialize the iteration number to be equal to 0. Here's the code for iteratively solving this nonlinear equation using the bisection method. This is going to iterate until the midpoint's absolute value is less than or equal to our tolerance epsilon, or until we have reached a total of 1,000 iterations. So you can see that in this case, 1,000 is the maximum number of possible iterations. If it goes beyond that, we will stop the algorithm instead of running it infinitely. So while the absolute value of the midpoint is greater than our tolerance and the iteration number is still below 1,000, we will first increment the iteration number by 1. And then we will compare the signs of fa and f of the midpoint. So if the first entry and the second entry of the fy vector, which is the length 3 vector, where you can remember the first point is the lower bound and the second one is the midpoint. If the product is less than 0, it means that they have unequal signs. In this case, we will set the upper bound to be equal to the current midpoint. So y3 is replaced with y2. And correspondingly, we replace the f evaluated at the upper bound with the f evaluated at the midpoint. If these two have equal signs, we will replace the lower bound with the current midpoint, and correspondingly, f of the lower bound is replaced with f at the midpoint. After replacing either the upper bound or the lower bound with the current midpoint, we will need to find the new midpoint for the new interval. The new midpoint, y2, is equal to the current y1 plus y3 divided by 2. And we will evaluate f at y2 given the a and n. And in addition to these, we will also store the sequence of the b0s and b1s, which is the sequence of the lower and the upper brackets in each of the iterations. So let's take a look at the results. First thing we can look at is how many iterations it took for the midpoint to have an absolute value below 0.0001. Well, we can look at the iteration number, it, and that's equal to 21. We can also look at the solution to the nonlinear equation, which is the midpoint in the last iteration. And that's given by the second entry of the y vector, and it's approximately 4.19. The corresponding f function evaluated at this y is really close to 0. We can also look at the interval, so the upper and the lower bounds for each of the bisection iterations. We started with the interval from 0 to 5n, which in this case is 0 to 100. And you can see that in each iteration, the length of the interval is cut by half. First is 0 to 100, and then it's 0 to 50. In the next iteration is also cut by half, and you can see this interval becomes narrower and narrower, and it tightens around the region close to 4.18. Well, since the nonlinear equation we're trying to solve is a quadratic equation, we can actually know the analytic solution to it using the quadratic formula. So if you recall from like maybe 10 years ago or maybe less than that, so when you were in middle school or high school, you have learned a quadratic formula where the solutions or the roots to a quadratic equation is given by negative of okay, so I'm not going to pronounce that, but I think it's negative b plus or minus the square root of b squared minus 4 times a and c divided by 2 times a, where a, b, c are the coefficients in front of the y squared, y, and the constant term. So in this case, for our given nonlinear equation, we can plug in these coefficients and we will find that the analytic solutions to this nonlinear equation is given by this formula over here. So you can see there are 2 real roots. And this simplifies to negative of a divided by n minus 1 plus or minus the square root of this thing inside. So let's try to find out what is the larger root of the 2. So negative a divided by n minus 1 plus the square root of this thing. And that's close to our solution of 4.186. You should note that there is another root which is around negative 4 point something. This root is outside the interval from 0 to 5n, so we're not going to find it.